Hello everyone. Today I'm going to discuss one very important topic with respect to undergraduate students, mostly second year students of electronics and communication engineering, and also other applied departments like electrical engineering, applied electronics, and instrumentation engineering. The topic is, as you can see, that fundamentals of coordinate system and vector calculus. So it is very much relevant that prerequisite required to understand that the subject electromagnetic theory and transmission lines. So we can say that that is the foundation for electromagnetic theory and transmission lines. So before moving on to the discussions, let's introduce myself. Myself, Dr. Surajit Mukherjee. I am working as an assistant professor at Department of Electronics and Communication Engineering of Haldia Institute of Technology. So let's jump into the topic. Now, why this is important that we need to understand very carefully. That the first point that is mentioned, that electromagnetic quantities are vector fields. So always we are dealing with some vector fields. Means vector fields means that the one has some magnitude, and along with that there is some directions. So the scalar field is applied on the circuits, but on the direction where it is matters, then we consider for vector fields. The second point is that we some of us already know about the Maxwell equations. If you are not know, then you will get understanding whenever you will study this subject later on. Anyway, that Maxwell equations is itself depends on the vector calculus, the solution of the vector calculus. So it is very much important to know that about the vector fields and the vector calculus. The third point is that the vector fields are expressed in different coordinate systems. So there are multiple types of coordinate systems. One is Cartesian, cylindrical, spherical, and many other also coordinate systems is there. But mainly three types of coordinate system we will deal with whenever we study this subject. And the fourth point, the most important point, is the transmission lines and the antennas on the field distribution part. That whenever we going to analyze that transmission lines or how the antenna radiates, so that is very much required for this kind of basic understanding on the vector calculus, on the coordinate systems, on the basic things. So the insight is that without this foundation, EM theory feels abstract and intimidating. So the foundation is very much important. Otherwise, whenever you will, as a student, so whenever you will going to study that electromagnetic field, so it will look like abstract, that you cannot understand something that you cannot visualize. Basically, that is the problem with this subject, that you cannot visualize that in which directions, in suppose in case of any circuits, you have used for diode or transistors or many digital circuits. So there you can find that okay, these inputs are given and outputs, you can everything you can visualize, but in this particular subject you cannot visualize things. So that is the main uh, uh, disadvantage, I can say, that to understand this subject. Anyway, if you have understand this fundamental things, then it will be very easy to go through it. What are the learning outcomes are there, that to going through these slides or going through these videos, uh, we can see that these are our understanding that coordinate systems used in EM, electromagnetic field, how coordinate system we can use. Uh, we can how we can represent the vector and fields mathematically, apply vector calculus for operators, interpret physical meaning of the divergence of curl. So that is very much important, that whenever we are dealing with the various mathematics related to the vector calculus or related to the Maxwell equations later on, then there is everywhere is a divergence, or either divergence or curl you have to apply. So that basic understanding is important. And the final point is that math tools to real EM phenomena. So these are we can say that divergence and curl. These are basically mathematical operations. Now, how it is related to the EM phenomena, that you have to understand. Now, in the right side there is an figure that it is written that transforming abstract mathematics into tangible physical understanding. Now, abstract mathematics is and a thing for what we can apply for the EM theory. Then it will be converted to some things that we can understand. So that is important. So the goal is that the mathematical confidence is required for understanding the electromagnetic theory. So calculus, the fundamental mathematics, you need to understand. Now, going to the first part, that coordinate system. Now, what is coordinate system? So if a space around us, some point on the space, then how we can define? So we can define some x directions, y direction, and z direction, as you can see that on the right hand side the figure. So it's a point P is xyz. So if you don't define that point, then how you can solve the problem at that point? So that's why there are some coordinate systems. So what is the function of the coordinate system? That a method to locate point in space uniquely identifies their position relative to an origin using numerical values. So with respect to the origin, we give x, y, we can find the value of x, y, and z. Next point is essential for defining field quantities. That is crucial for solving EM problems that process specific geometrical symmetries. Now, going on this, you can understand that how these specific geometrical symmetries will be applicable for various problems in the field of electromagnetic theory. So the commonly used are that Cartesian systems, the also sometimes it's called as a rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. The first one is the Cartesian or rectangular coordinate system. To define it as a x, y, and z, just like the previous figures, a point P is x, y, and z. Now the unit vectors we define is x, a suffix x, a suffix y, and a suffix z. So some students, whenever we gives understanding in the subject, some students from mathematical background from class 12, that they used to apply ijk. So ijk is okay, there is no issue with the ijk because just letters we are representing ijk, but the convention is whenever we study this subject, the convention is that x, y, and z. Therefore, if you use ijk, then you have to write ai, aj, and ak. Okay, and there is a position vector from the origin to that point. So that we can write it as that x ax, x means the value of the magnitude of the along x direction. So y is the magnitude and the y direction, and z is the magnitude of the z direction. And ax ay, as we know, that is given the vectorical directions. So where we can apply this rectangular coordinate system? We can apply this in rectangular or planar. For example, parallel plates, rectangular waveguides. So rectangular waveguide, you may not have known those things. So whenever you study this subject in the transmission line part, there is a rectangular waveguide part. So there, to solve the problem, we have to apply that Cartesian coordinate system. As just mentioned that the EM applications, the parallel plate capacitor, we apply Cartesian coordinate systems. Rectangular waveguide, that is a shape of rectangular, so we can say as a rectangular pipe for hollow metallic pipe for your basic understanding. So through that pipe we send electromagnetic wave. Now how the wave is behaving inside that pipe, that we can understand through the solution using Cartesian coordinate system. A uniform or planar transmission lines and PCB and IC interconnects. PCB means that the circuit board is used in various electronic devices. So that circuit board, so whenever we are going for very high frequency, that we have sometimes the electromagnetic fields are very much uh, crucial to understand the electromagnetic fields through that printed circuit board or IC. For example, that your mobile phone is say 1.6 gigahertz processor, or your computer has 3 gigahertz processor. Now at that speed, the at that frequency, you can understand that there should be some electromagnetic fields, and that electromagnetic fields should be mitigated. And to understand that, you need to understand the Cartesian system, or that coordinate system. So next is the cylindrical coordinate system. The cylindrical coordinate system is sometimes there is a cylindrical shape of nature where we try to solve that electromagnetic problem. Now that coordinate system is defined as rho, phi, and z. So rho is basically that the if we consider a cylinder like this, just a minute. If we consider the cylindrical structure like this at this point, so my actually I'm using mouse, so it maybe looks like odd. Anyway, that the radius of the cylinder, just for basic understanding, the radius of the cylinder is defined as the rho, and the phi is the that point, that projection of the rho, and the angle between the x-axis. Okay, and z is along the z direction. So these are the basic fundamental directions for this coordinate system, which is known as the cylindrical coordinate system. And one position vector can be defined as like this. So where we can apply it? So the problems with the axial symmetry, that's just like coaxial cable or long straight wire or circular waveguide. Circular waveguide is one kind of waveguide, just like previous I told you that rectangular waveguide. Similarly, circular waveguide is present. Coaxial cable, you very much known that earlier the cable TVs, or the cable which is connected with the your rooftop dish TV antennas to your set-top box. That is also a that is known as the coaxial cable. So for solving the problem, or for solving the electromagnetic field for that cable, we need to apply this cylindrical coordinate system. That mentioned coaxial cable fundamental transmission line theory, it is applied, involve outer and inner conductors, hollow metal pipes, circular waveguides, already mentioned, current carrying wires, so there is a current through any wires, and magnetic fields, or the Ampere's law, you may have known this Ampere's law. So there we apply that cylindrical coordinate system. And next is the spherical coordinate system. The spherical coordinate system is like a spherical structure, like a ball. Any point over the ball, and we try to find out that the field over that point. So there we need to apply this spherical coordinate system. So there are three quantities: r, theta, and phi. So r is the distance, phi just previous case, that the projection of r making an angle with the x-axis, and theta is the angle with the z-axis. That r line is making an angle with the z-axis, that is known as the theta. So that is r, theta, and phi, and the unit vectors ar, a theta, and a phi. Position vector r, ar, you can define this like this. So for which case it is applicable, that point charges, antenna radiation pattern, far field analysis. Mostly in antenna, we use the spherical coordinate system. Point charges, antenna radiation pattern, EM wave propagation through some spherical surface, and the far field analysis of the antenna. For that also we use that spherical coordinate system. So this is the brief summary of that first part of the coordinate system, that is symmetry, box-like geometry, that is for the Cartesian coordinate system, tube-like geometries for cylindrical, and ball-like geometries for spherical coordinate system. The variables x, y, z, rho, phi, z, and r, theta, phi for three different cases. Primary use already mentioned, that Cartesian is used for transmission line, rectangular waveguide, PCB traces. Cylindrical is used for coaxial cable, circular waveguide, and straight wires. And spherical is antenna, point charts, radar cross sections. So mathematical complexity is for spherical is higher, and for Cartesian it is simpler. So what is the key takeaways? That choosing the right system aligned to the geometry with the mathematics turning complex partial differential equation into simpler ordinary differential equations. So you have gone through differential equations in your mathematics. So complex partial differential equations can be simplified into ordinary differential equations through the knowledge of the coordinate system. So this is the basic fundamentals requirement to understand this coordinate system. As mentioned, that choosing the right coordinate systems, how to approach the EM problem that match the geometry, that for the geometry we are going to solve, that for that which kind of coordinate systems is required. Exploit symmetry if the field is constant along the specific dimensions. Use the system like reflects the invariance. Simplify Maxwell equations. Then we have to partial differential equations to simply ordinary differential equation, and it reduce the computational effort, minimize the number of field components needed to describe the solutions. So the golden rule of EM theory: right coordinate system, simpler math, right?